Lab 3, determining the mass. The objective of this lab is to determine the mass of a black hole using given position data in the form of a CSV file of a nearby star. In order to determine the mass of the black hole, we must apply Newton's second law to the computation. I determined the mass of my black hole to be 7.99 e to the 38. So here are the key physics principles to note. Velocity is change in position over change in time. Change in velocity is final minus initial. So we use these formulas over the course of the entire data set. Change in momentum is change in velocity times mass of the star. Fnet will be represented as change in momentum over change in time. Fnet can be broken down into the parallel and perpendicular components. dp/dt can also be broken down into the parallel and perpendicular components. So we simply take these formulas and introduce them into our Python code to produce the trajectory of our star around the black hole. In order to calculate for the mass of the black hole itself, we use the gravitational formula, which is equal to g times the mass of the star times the mass of the black hole all over r squared. G in this case is a constant, 6.67 e to the negative 11. So here I have my Python code. So as you can see, I introduced a black hole attribute to create a visual representation as well as the star itself. The mass of the star was 2.76 e to the 27th with the black hole position given as well. I created a black hole total mass to calculate the average, just in case the black hole mass given to me wasn't quite accurate. I also used a t-step set to 1 to determine the length of the position data set. Delta t was represented as 86,400, which is also equal to 1 day, t set to 0. Here is where we determine the velocity from our data. And down here we have the loop, which calculates Fnet, also momentum. As you can see, V initial, V final, momentum initial, momentum final. So in this case, we simply use the formulas and translated them into the Python coding. Delta V, delta P. Down here we have dp/dt, which is equal to delta P over delta T, as we said before. Fnet is also equal to dp/dt. P hat. We also determine dp/dt parallel, and we set that equal to Fnet parallel. In order to determine dp/dt perpendicular, we subtract the dp/dt parallel from dp/dt. And down here we have the arrows, which represent the parallel and perpendicular, and as well as the momentum. And we also have the mass formula, the gravitational formula, rearranged to give us the mass of the black hole itself. So here is my trajectory or my model. As you can see, the model displays the trajectory of the black hole represented in the black in the star, but I had difficulty representing my parallel, perpendicular, and momentum forces. The black here is the parallel, but as you can tell, that's not actually accurate. I checked my coding, everything seemed correct. I just could not, for the life of me, figure out what. I do believe that it was my CSV file because I tried everything, including changing the arrow scale. So there you have it. So let us answer these questions. What does it mean? How are Fnet parallel, Fnet perpendicular different from dp/dt, dp/dt parallel and perpendicular? So dp/dt can be calculated from our observations, which are in this case, the given position data set. Fnet is simply the net forces acting to create the motion. So Fnet cannot be calculated as a quantity. So Fnet would actually be qualitative, whereas dp/dt would be quantitative. And for the last question, what if, assume the motion of the observed star remains unchanged and is affected only by the gravitational force of a new black hole? Could you tell the difference? In other words, is it possible for you to find the value for the mass of the new black hole that is different from the mass you found for the original? If we were to assume the motion of the observed star remained unchanged, then the mass of the black hole, or the star, would not change. So, let me rephrase that. If the motion of the observed star remained unchanged, then the mass of the black hole would simply be the same. So we would not be able to tell the difference. It would, in other words, it'd be the same black hole. So no, we would not be able to determine that it is a different mass from the original black hole. This is my lab 3. Thank you.